In the last lecture we have seen how to draw the nuclear shell model, and in this lecture we are going to see what are the physical significances or what are the advantages of the nuclear shell model, and what are its limitations. By using the nuclear shell model, we can calculate the spin parity of any nucleus. Now what is meant by a spin parity? See here. Here in nuclear and particle physics we use the term spin not for the spin angular momentum but for the total angular momentum of the nucleus. So total angular momentum is nothing but the spin of the nucleus. And what is the parity? So the parity is the wave function related to this total angular momentum. Just like we see that spin of the electron is plus 1/2 or minus 1/2. Similar to that, the total angular momentum or the spin of the nucleus is either positive or it is a negative. So this L is equal to even, the parity is said to be positive, and this when L is equal to odd, the parity is said to be negative. Now let us have an example of the even nuclei. Now what is mean by even nuclei? The nuclei which is having even number of protons and even number of neutrons is called as a even nuclei. Here P is equal to 8, N is equal to also 8. So this is called as a even nuclei. So let us calculate the spin parity of the even nuclei. We already know how to draw this energy level diagram. First is a 1s 1/2, 1p 3/2, 1p 1/2, then 1d 5/2. Up to here is okay. So on the left hand side it's proton, right hand side it's neutron. So 8 protons are there. We know that s orbit will consist of 2 protons, 4, then 2. So here is the 8 protons are filled. Similarly 8 neutrons could be filled, and here we can see that no unpaired nucleon is remaining. Therefore the spin parity of the nucleus is 0 plus, which is written as J pi. J is a spin, parity is positive. So for all even nuclei, the spin parity is 0 plus. For all even nuclei, spin parity is 0 plus. Similarly, if I take odd even or even odd, it is sometimes said. For odd nuclei, or it is also sometimes said as a even odd nuclei. So when we take the odd even or even odd nuclei, for this the spin parity can be calculated. For example, if I have 8O17, we are just changing the same example. So if I take the same energy levels, so 1 is 1/2, 1p 3/2, and 1d 5/2. So number of protons is 8, which is even, and number of neutrons will be 9, which is odd. So it is even odd nuclei. So I'll write it here, proton and neutron, 2, 4, 2. So 8 protons will be there, and 2, 4, 2 and 1. So for this 8O17, one unpaired neutron is there, and this one unpaired neutron will decide the spin parity of this nucleus. So I can write here the spin parity of this nucleus will be 5/2 plus. We know that for D, L is equal to 2, which is a even number, and when L is even, the parity is positive. Similarly, we can calculate the spin parity of the excited states. Nearly 2 MeV, or from 1.5 MeV to 2 MeV, this much amount of energy is required for the breaking of the pair of the proton and shifting it to the next excited state. Okay, now if somehow I am able to supply 2 MeV amount of energy to this nucleus, so what will happen? So the neutron, which is unpaired here, so this will jump from this state to this state. Now which is the next state, which is 2s 1 half. So the spin parity of the first excited state, so the ground state spin parity was, ground state spin parity was 5 by 2 plus. Now the first excited state will be 1 half plus, as for s l is equal to 0, therefore the parity will be positive. Now we can see that with the help of this nuclear shell model we can explain ground state spin parity of the any nucleus, and we can also explain some excited states also. But some excited states are not well explained with the help of this nuclear shell model. Okay, this part is a advantage or the physical significance of the nuclear shell model, which means that you can calculate the spin parity of the any nucleus, and along with this you can calculate the spin parity of the excited states of the nucleus. So this was all about the physical significance or the advantages of the nuclear shell model. There are some limitations for the nuclear shell model which can be overcome by using the collective model, by combining the nuclear shell model with a liquid drop model or rotational vibrations. There are some limitations of the nuclear shell model, like some excited states cannot be explained by using this nuclear shell model, or the nuclear shell model says that the spin parity is decided by only the unpaired nucleon. Okay, for the same atom or for the same nuclei, we can see that here 8O17, the second excited state observed was one half minus. Data for the nuclear shell model says that the second excited state spin parity is 1 half minus. Now in this figure, how we can get the second excited state? So the second excited spin parity can be given only if the neutron from this 1p 1 half is jumping to 1d 5 by 2, and here one unpaired neutron will remain, and it will give me the spin parity of 1 half minus. P L is odd, therefore parity will be negative. So therefore the spin parity of the unpaired neutron, that only can give me the 1 half minus, which says that only unpaired neutron is not responsible for the spin parity. So this is the first limitation of the limitation is there are some nuclei which are having the same ground state spin parity and same excited state spin parity, but there is a large energy difference between the first excited states of the two. Okay, I'll show it here like this. Okay, so in both the cases, if you try to draw the nuclear shell model like this, you will find that for both the nuclei, the exchange particle is neutron, the ground state is same for the ground state spin parity is same for both the nuclei, and the first excited state also will be same for these two nuclei. Okay, so let us just draw this diagram. So this is Ca 2021. So here it will be proton and neutron. Here we can see that neutron is more than this proton. So these all protons will be paired up. So the exchange particle will be neutron. Same will be the case for here. Here are the 20 protons are there, and the unpaired nucleon will be neutron here also. So in both the cases, the exchange particle will be neutron only. So for this 2, 4, 2, then 6. Sorry. So here it will be 1s 1 half, 1p 3 by 2, 1p 1 half, 1d 5 by 2, 2s 1 half, 1d 3 by 2. So let me draw it properly. So this is the case of the Ca 20, 21, 41, and this is the energy level diagram for the 20 Ca 23, and this will be 42, 43. So for both the energy diagrams, we can see that the exchange particle is a neutron and the exchange particle is in a 1f7 by 2. Therefore, the spin parity of the ground state nuclei will be 7 by 2 minus. Now, if I supply nearly 2 MeV amount of energy, it will go to some excited state, and the first excited state for both the nuclei will be 2p3 by 2. Okay, therefore the spin parity of the first excited state should be, so it should be 3 by 2 minus. So for both the nuclei, the exchange particle is a neutron. Ground state spin parity is 7 by 2 minus, and the first excited state spin parity will be 3 by 2 minus for both the cases. But the energy difference between these two is different. Even if the ground state and excited state spin parity are same, even if the exchange particle is neutron, there is a difference in the first excited state and the ground state energy for the both nuclei, and this cannot be explained with the help of this nuclear shell model. So if you consider the nuclei of the orgon, which has 18 protons and 20 neutrons, and if I draw the energy level diagram for the orgon, we can see that all the protons and all the neutrons are filled up and paired up with each other. Therefore the ground state spin parity will be 0 plus. Now the experimental data says that the first excited state is at a 2 plus, then the second excited state is at 3 minus, and then we are going to get 2 plus. So by using the nuclear shell model, we cannot give these energy levels like 3 minus and 2 plus, but when we combine this nuclear shell model along with the liquid drop model, we can explain these excited states like 3 minus and 2 plus. So the spin parity 3 minus can be explained by jumping of the neutron from 1f7 by 2 to 2p 3 by 2. And how it is written? So it can be given by 7 by 2 plus 3 by 2 to 7 by 3, 7 by 2 minus 3 by 2. So the combination of these angular momentums can give value from 5 to 2. So it may give value from 5, 4, 3 and 2. As the neutron is jumping from 1f to 1p orbital, so for p, L is odd and therefore the parity will be negative. So it can give the angular momentum as 5 minus, 4 minus, 3 minus and 2 minus. Okay, so by using this nuclear shell model along with the liquid drop model, we can explain some excited states of the nuclei. some energy levels are seen, or the some excited state spin parity could be seen as a 2 plus, but these 2 plus are below this 2 MeV. Okay, so this is the excitation of the neutron or the proton from one energy level to the another energy level, and this requires the nearly 2 MeV. Okay, but some excited states are seen below this 2 MeV, which means that they are not due to the jumping of the neutrons or the protons from one energy level to the another energy level, and these energy levels could be given by the collective model. So what is meant by collective model? When you combine the shell model with the vibrational or rotational. So when you combine the shell model along with some another model, then these are called as a collective models, and these extra energy levels could be explained with the help of these collective models, and these collective models which we will see in the next lecture.